Hi guys. Today we're starting to solve trigonometric equations. Before we talk about our new topic, I want you to take a minute and try to solve the equation 5s is equal to 3s plus square root of 3. Go ahead and pause the video until you get your solution. And then for question number 2, I want you to pull out a unit circle and try to find an angle such that it has a sine value of square root of 3 over 2. Pause the video now and work out the two problems. You should have gotten solutions. For number 1, you should have been able to find that s is equal to square root of 3 over 2. Well, what if I told you that s really represents or stands for the sine of x? Now we have that the sine of x is equal to square root of 3 over 2. If I'm trying to find x, really I'm looking for an angle which has a sine value of square root of 3 over 2. This is indeed what you guys were trying to find in question number 2. In question number 2, you were trying to find an angle, x, such that its sine value is equal to square root of 3 over 2. If you were thinking in degrees, then I'm sure you were able to find that 60 degrees indeed has that sine value. However, this is not the only angle that has this value. In addition to 60 degrees, 120 degrees also has a sine value of square root of 3 over 2. Now let's go ahead and move on to actually solving trig equations. Go ahead and pick up your notes. We're going to record 5 different examples. Each example shows a different type of problem that you might encounter. Example number 1 says that we're going to find all solutions of a trigonometric equation. And we're given an equation which is 5 times sine of x is equal to 3 times sine of x plus square root of 3. I don't know if you noticed, but this is the very same solution as what you had to complete in the warm-up question. The difference is that instead of s, this one uses sine of x. Now sine of x, remember, in this case is just representing a numerical value that is written in a more complex way. So one strategy that you can use is rewrite it as we did in the warm-up. So you can rewrite this as 5s is equal to 3s plus square root of 3. And then you can find that s is equal to square root of 3 over 2. At which point you would have to replace the s with sine of x is equal to square root of 3 over 2. Okay, now you can use the unit circle to figure out what are those angles that have a sine value of square root of 3 over 2. Well, the sine is my y-coordinate, so square root of 3 over 2 happens at 60 degrees, or pi over 3. Since it is the y-coordinate, if you draw a horizontal line straight from the first solution that you found, you can find your second solution as well. The second solution is 2 pi over 3, or 120 degrees. This is just one strategy of solving it. The second strategy of solving the same equation is keep the sine of x, simply treat it as a variable. So now we have 5 sine of x plus 3 sine of x. Actually, this is supposed to be an equal. 5 times sine of x is equal to 3 times sine of x plus square root of 3. And then you want to get your sine of x to be on the same side, so you'd have to subtract 3 sine of x. That gives you 2 sine of x is equal to square root of 3, or the sine of x is equal to square root of 3 over 2. We're getting the same answer as the first time, we're just working out in a different strategy. Now for each one of those, to find that angle, really you're solving x is equal to the sine inverse of square root of 3 over 2. Now, so far we have found two solutions, and those were x is equal to pi over 3 and 2 pi over 3. But consider this. What if I made a full revolution before I came up to 60 degrees? That sign value would be the same. What if I completed 2 or 3 or 5 full revolutions before I came up to 60 degrees? That would still have the same sign value. Not just that, but I can complete the revolutions in the negative direction as well. We need to be able to incorporate all solutions in this problem. So for all solutions, we actually have to add each revolution or each period of that function. Sine of x has a period of 2 pi, so we would have to add n times 2 pi plus n times 2 pi. For this one, please note n is an integer or a whole number. That gives us all the possible solutions, not just on the unit circle, but from negative infinity to positive infinity. Now let's go ahead and take a look at the next example. In the next example, we're solving an equation with a multiple angle. Our equation is tangent of 2x is equal to square root of 3, where x has to be limited between 0 and 2 pi, or the angles that we find are really going to be on the unit circle, no additional revolutions. Okay, well, to solve this, then I'm solving for 2x is equal to the tangent inverse of square root of 3. Or, what are the angles that have a tangent of square root of 3? Well, if you look at, remember that the tangent is the ratio of y over x. So if we check at 60 degrees again, then the tangent is square root of 3 over 2 divided by 1/2. So it is square root of 3. Pi over 3 is one of our answers. We get that 2x is equal to pi over 3. However, we know that these values repeat, so when is the next time that we will have the same tangent value? Well, if we look at the second quadrant, y over x is going to be a positive over a negative value. This tangent is negative square root of 3. Let's look at the third quadrant. In the third quadrant, we have negative divided by a negative. This will be positive square root of 3. That means that our second answer is that 2x could also be equal to 4 pi over 3. Now note that sometimes I reference the angles in degrees. However, all of the solutions should be given in radians at this level. So you can think about the angles in degree terms, but when you're giving your final answer, just make sure that you convert into radians. So now we took whatever was inside of the tangent and we set it to equal the degrees or angle measurements that have a tangent of square root of 3. We're still looking for x by itself. It comes down to solving this equation, which is linear. We have to divide both sides by 2. We get x is equal to pi over 6. And x is equal to 2 pi over 3. So those will be our two final answers. Here, once again, we're limited to just one unit circle. We're not looking at any additional revolutions. Let's take a look at the next problem. This is example 3 in your notes. You are solving a trigonometric equation in quadratic form. It says solve the equation 4 cosine squared of x minus 3 is equal to 0. If it looks too complex and you're not sure where to get started, you can always write over to the side and you can say, whoop, bad color. You can say, let cosine of x equal to c. Then you're left with 4 times c squared minus 3 is equal to 0. Can you solve this quadratic equation? Absolutely. You have to add 3 to both sides, then you divide by 4. That gives you that c squared is equal to 3/4. How do you get c by itself? You are correct. You have to take the square root of both sides. Please don't forget that leaves you with c is equal to plus or minus the square root of 3/2. I'm going to go back and rework the same problem with cosine of x. But I want you to see that using the substitution for your trig value, just call it one letter, makes your equation look much simpler and your brain can handle it much easier that way. If you treat cosine of x as a variable, then you're still going to use the same inverse operations. You're going to add 3 to both sides because your goal is to isolate cosine squared of x by itself. That gives you 4 cosine squared of x is equal to 3. Then you're going to divide both sides by 4, and you have cosine squared of x is equal to 3/4. At this point, we can take the square root of both sides, and we have that cosine of x is equal to plus or minus square root of 3/2. Good. Now to solve this basic trig equation, we're asking ourselves, what are the angles that have a cosine of positive square root of 3/2 or negative square root of 3/2? Our angles, x equal to, let's go ahead and start with the positive ones. Cosine is our x-coordinate, so I see positive square root of 3/2 at pi/6 right here. I see negative square root of 3/2 at 5 pi/6. Then another negative square root of 3/2 at 7 pi/6. And then there is a positive square root of 3/2 at 11 pi/6. So to give our answers, we have x is equal to pi/6, 5 pi/6, 7 pi/6, and then 11 pi/6. Note that 2 of those answers belong with the positive cosine result, and 2 of those belong with the negative cosine result. But we ended up with 4 separate solutions, and our original equation was in quadratic form. All right, we just have 2 more. In example number 4, we are going to use factoring to separate the different equations. A lot of students are tempted to divide both sides by sine of x. We're not allowed to do that because sine of x could be equal to 0, and we're not allowed to divide by 0. So instead, we're going to transfer the sine of x to the left-hand side. In other words, we're going to subtract sine of x from both sides. Minus sine of x, minus sine of x. That gives us sine of x times the tangent of x minus the sine of x is equal to 0. Now we can actually use the tip in the example. It says use factoring. So I'm going to factor out sine of x, and in the parentheses we're left with tangent of x minus 1 is equal to 0. Well, the only way that this product, sine of x times tangent of x minus 1 is equal to 0 is if either sine of x is equal to 0 or the tangent of x minus 1 is equal to 0. That's when you go back to your unit circle and you figure out, when is the sine of x equal to 0? Well, it is when the angle is equal to 0 or the angle is equal to pi. For the next equation, we have tangent of x is equal to 1. That happens when the angle is equal to, or x is equal to pi over 4, or 5 pi over 4. So we're going to be in either the first or the third quadrant. And this right here is our final answer. Once again, we have 4 solutions for this one, 2 for each of the factors that are equal to 0. Let's go ahead and take a look at the last example. Here we have to use our calculator. We're asked to solve the equation correct 4 decimal places for just 1 revolution of the unit circle, and we're given that the tangent of x is equal to 3.1044. Well, there's no way that we can figure that out simply by using the unit circle. However, we're looking for the angle, so now we can rewrite it as an inverse function. And we have that x is equal to the tangent inverse of 3.1044. So this is when we switch back to our calculator. On the calculator, you can input tangent inverse of 3.1044, and you would get an answer. My calculator is currently in degree mode, which means that the answer that I got is giving me a solution in degrees. My angle is equal to 72.145. Okay? It is somewhere around, I don't know, somewhere around here. This angle is somewhere around here. But the calculator will only give you one solution. Is it possible that there is another angle with the same tangent measurement? If so, which quadrant would it be located in? If you said quadrant 3, then you were correct. In quadrant 3, this reference angle will have the same tangent value. Okay? So your calculator is only going to give you one solution, but you should be able to use your knowledge of trig to give the second solution. And that solution is 180 degrees plus the found reference angle. So that adds up to 250 degrees, 0.145. Okay? So now we have 2 solutions. I want you to please add yourself a note on here and take note that calculator will only show you one solution. You have to find the second one. Use reference angles. To find the second solution. Okay, that's all I have for you. From here on out, we are going to go ahead and practice several strategies on your own.